All right, hello everyone. Yeah, as I said in yesterday's video, that this year I'll be trying to do all the Kickstart rounds, and we're at around A right now. So it's gonna start in 1.5 minutes or something. So yeah, I won't be doing the screencast plus commentary. I'll be just doing the screencast, and the solutions I'll discuss later. And yeah, just the thing, like I wanted to show that I added this part in my code because yeah, this will be useful today. You see, you have to print the output something like this. Uh, like there are multiple test cases, and then you have to print them like with a test number, something like this. This is required in Kickstarts. Uh, Maybe you have seen similar thing in Facebook Hacker Cup as well. But anyway, so the round is about to start, and I won't be putting on the mic on me because like sometimes like during contest I go up and walk around. So this is like a binding thing, you know. Yeah, I don't want a binding contract on me. That's why I'm going to keep it aside, and I'll put it on while I'm discussing the solution because it's not like I'll be picking anything important. So yeah, let's start the round and. We'll see. Like I'll see you after that. Okay. Okay, 27 right now. 27 rank. My last penalty was like I did one penalty. This wrong answer. This was like pretty stupid thing. Like a really dumb thing. Very dumb mistake. So basically, in this last problem, it's something like we're making a spanning tree from a graph, right? Maximum spanning tree. So the mistake that I did here was it's like I was using the PIMS algorithm for PIM or PRIM. I think it's PRIMS algorithm, right? So I was using the PRIMS algorithm for the maximum spanning tree, and let me see if the mic is on. Hello, hello. Right. Yeah. So what I did was instead of I didn't really check if the graph is connected or not. So it's like instead of the maximum spanning tree, it could be in the maximum spanning forest. And what I did was I just made the tree for like one of the connected components. Right. So that's the mistake that I did. It was pretty stupid, and it gave me wrong answer. I think I spent then 6 minutes trying to figure out what's the flaw in my logic. So I like, I mean, I made so many sample test cases. I make so many sample test cases visible. Yeah. So I tried to make so many. I scribbled a lot. Tried to make so many sample test cases just to figure out what's the flaw in my logic. Then I realized that there's no flaw in my logic. Out of nowhere, I just realized that yeah, I'm just not considering if it's disconnected, if the graph is disconnected. So then I fixed that and got it accepted. If I hadn't done this dumb mistake, I would have been somewhere, I think definitely higher than this. Maybe not here at least. How much do they add for the penalty? 4 minutes? Right, 4 minutes for the penalty. So I would have been at the same point. No, wait a minute. This person had some penalty. Right. So I would have been 26th, I guess. Yeah. But then, no, not 26. I would have ended at 105. Yeah, I would have been 24th. So, yeah, that's fine, I think. Although somebody can still beat me if they finish before 115. No, I think they can't beat me now. Like, anybody who beats me within 10 seconds can beat me. Okay, two people already beat me. So, 29th definitely would have been above them. But yeah, I think it's over now. Now nobody can surpass me. Because like even if somebody does it with zero penalty, the last submission will count. There will be like 1 hour and like definitely more than this. Definitely more than 1 hour 15 minutes 36. Right. So yeah, my final rank is 29th. Mm, right. I think I wasted a lot of time on this B. Yeah, 18 minutes. The other people, some took even longer than that. Maybe I wasted my time a lot on D. I should have realized early that it's just MSc. Okay, so I think now we can discuss the solutions. Uh, okay, right. By the way, in today's contest in this Kickstart, like so many problems were based on that 2D matrix. Like almost every problem, I think only first problem didn't have 2D matrix, and every other problem had a 2D matrix in it. That's something worth noting. Hmm. By the way, did I finish the contest in like 1 hour 10 minutes? Yeah. So what's my India rank? Is it 5, 6, 5? Second. Oh, India rank 2. Yeah, that's nice. Only Aryan C403 beat us, and yeah, he's a friend, so that's fine. Okay, so India rank 2. That's my best India rank in a Kickstart round, and my second best global rank in a Kickstart round. My absolute best was, I think, Kickstart round D 2020 when I got 23rd rank. Anyway, so let's see the solutions now. Let's start with K goodness string. Yeah, so this was pretty trivial, as I said in yesterday's video also, that the first problem is usually not that tough. It's really easy. I spent 3 minutes on this because I kind of didn't believe it's that easy. So I was trying to recheck my logic, but yeah, it's just that. So basically, what we want to do is we want like um, we will make the. Let's read the statement. I kind of forgot it a bit. Right. So we want a goodness score of k, and goodness score is defined as the number of indices such that this thing holds to. And what this thing means is just that you want the mm, like if the first and last character are not equal, you get one score. If the second last and the second character are not equal, you get one more score, and so on. Right? The central character is not considered for odd strings. For even strings, the first half characters are considered. So like if this is not equal to this, you can do it, right? So something like that. And you want to make the score equal to k, and I think it's always possible to do it because k is smaller or equal to n by 2, right? It is always possible to do it. You just want to make the minimum number of changes in the string, right? So for that, what we can do is we can just calculate the score of the string right now, and we know that in one move we can either increase the score by 1 or we can decrease the score by 1. We can do any of those two depending upon what we want, right? So what I mean to say is something like let's say here, like if you want to increase the score here, what I can do is I can make this b into a, like I can change this b and make it a a. So yeah, I get all a's and my score is 0. So that's how I can decrease the score. And like if I wanted to increase the score, I could have changes this a to anything other than a's, like x, y, z, p, q, anything, right? So yeah, that's what it was. And yeah, let me show you my code to this one. Okay, so sorry. Yeah, so I take n and k and the string as input. I keep a count. This is basically storing the score of the current string without any changes. And this is just I'm checking the like ith character with the ith last character. And if they are not equal, I'm increasing the count by 1. And my answer is just the absolute difference between count and k, because like in one move I can change the answer by 1 as I please, right? So the answer is just absolute difference of count minus k, and I print answer, right? So this was easy. Now second problem, it was also easy, but I at least the way I implemented it, the implementation was kind of, like I didn't like it much, but I'll explain the central concept behind it. Okay. Mm, Pretty sure I could have done it in an easier way, maybe like I don't know, something like maybe looped on all the directions instead of writing all this code. But anyway, I'll tell you what this is. So this is mainly like an implementation problem, not a lot of stuff that you're doing. Maybe something like prefix sum a little bit. Not exactly prefix sum. Something like, yeah, we'll see. Okay. Now basically you are given a grid like this, R rows, like R rows and C columns. Okay. And what you want to do is you want to count the number of L's that are present there. Okay. So like these are L's, L, capital L of the English, in any direction it can be. And these are the conditions for something to be L. So each of the segments in it must be good segments. So like the grid that you're given has either 0 or 1. So 0 is like a blank space. 1 is like a occupied space, and you want some of the occupied spaces to make a 1 and sorry, make a L. and a segment is called good if all the cells in the segment contain only one, right? So it's like this is a good segment, this is a good segment, and so on. So you want to join the good segments to make the L, and you can see that the two segments must be perpendicular to each other. Like obviously you cannot have a straight line, that won't be L, and the segment must share one cell that is the endpoint of both segments, right? So you like they should share one cell and it should be endpoint of both of them, right? So like this won't work because they are also sharing one point, but uh, it's not the endpoint, right? So only the endpoint should be shared, and segments must have length at least 2, right? So this is important. The segments must have length at least 2. Like a single dot won't help, right? So like this should be at least 2, this should be like the smallest side should be at least 2. Now the length of the longer segment is twice the length of the shortest segment, right? Like if this is 2, this should be 4, if this is 3, this should be 6, and so on. So you can see even here as well that this is 2 and this is more than 4, so it is invalid. This is 3 and this is the like less than 6, so it is also invalid, and so on, right? So whenever it's something like they're not same, whenever it is not the double of that thing, it is invalid. And yeah, so that's it. You want to count the number of L's, and these segments don't have to be maximal. You can see that even if there is there are a lot of ones continuously, you can pick a subset of them and make L from that, right? So it's not like beyond the L there should be a 0 or something like that, right? So that's not a requirement, and that's what you want to do. So let's see what I did here. So first of all, there were a lot of directions in this. Like you can have a L like this, you can have the L like this, or like this, or like this, or this. Basically, so many ways to make the L's, and that's why it took me a lot of code to do it all, because I kind of wrote the code for all of this separately, right? So I wrote the code for all the directions separately. Maybe there is a way to kind of loop through something the directions and everything, so that you're able to do all that without that much hassle. One thing that I just now realized, what we could have done is we could have kept on rotating this entire matrix, like just do the calculation for else in the one direction and keep on rotating the matrix so that you get the else in all of the direction, right? So just by getting this, we also get this and this and this and this, right? So we get all four of these, but we still don't get this, and so on. So what we can do is we can flip that. So basically what we wanted to do is we wanted to get the L's in only one direction, like only this type of L we want to find. But what we will do is we will keep on rotating the matrix 4 times, and after that we will flip the matrix once. Flipping means like this. So this is like a rotation, this is a rotation, and this is a flip. So what we wanted to do is we wanted to flip the matrix once and we wanted to rotate the matrix thrice, and solve for this shape of L every time. Although I didn't realize this thing, and probably it would have taken me a little more time to do this thing. So what I did is I just wrote all 8 cases, and I made all types of L's. Right. So in here I'll just explain how to make one type of L, and I'll just explain this type of L. Right. So I'll just explain this type of L, how to make this. Right. So this type of L, what we will do is we will iterate on this joining point, and for each joining point we will see how many times sorry, for each joining point I will see how many type of how many L's of this type are present there, right? So something like that I want to do, and let's say I have a lot of cells that are occupied like this, right? I have a lot of cells like this, and I want to make this type of L, right? So this should be the shortest side, this should be the double of that side, and they should intersect here and so on, right? So something like, right, so if this is like, you can see this is 6 and this is 7. So the biggest L that we can make is of size 3, because we'll take these 3 here and then we'll take these 6 here, like these 6 and these 3, right? So that's the biggest L that we can make. We can make slightly smaller L's also. Like if we can make 3, we can definitely make 2 also, right? We could make 1 also, but 1 is not valid. So it is given in the problem that where is it? Segment length must be at least 2. So even the smaller should be at least 2, and that's it. So what if we already had how many ones we have to the left of this and how many ones we have to the up direction of it, like to the top? So if we already knew that we have like 6 ones to the left and 7 ones to the top, what we could have done is we could have taken the minimum of 6 comma 7 by 2 and subtracted 1 from it. So this is the number of L's that we can make here, because you can see that the minimum of 6 and 7 by 2. So, or like the minimum, the 7 by 2 is equal to 3. That means we can take 3 from here and we can take 6 from here, right? There could have been a case when this was very, very long, but the 6 would have been the bottleneck. So then the 6 would have worked. We're subtracting 1 from here because the segment of length 1 is not working, right? So here you can try. This will give you minimum of 6 comma 3 minus 1, which is 2. That means we can make 2 L's, and indeed we can make 2 L's because we can make this thing and we can make this thing, right? And that's what we had to do. So to do the same thing in all the directions, what you can do is you can rotate the matrix 4 times, and then you can flip it once and then rotate it again 4 times, right? So that's not a lot of code, and every time you just find this type of L and it will work, right? So you would have done something like that, or I think you didn't even have to rotate. Sorry, it had to rotate. I think you didn't even have to flip it, because what you could have done is you could have taken this like this is 6 comma 7 by 2. So you also take minimum of 6 by 2 comma 7 and do minus 1. So if you do this step also, you don't even have to flip it, right? So I think that's still a little more code. Flipping is kind of easy. So what you guys have done is, like, I think that's the easiest way to do this, and it's a good programming practice also. It didn't click me during the contest, but if it had, then I would have done it quicker. So yeah, that's it. You want to rotate the matrix in all directions, and then you want to flip it once and then again rotate it, and each time just find this type of L. And now you can see my code a little bit. I did for all directions individually. So like I have this 2D, sorry, yeah. So I have this 2D matrix for left, right, up and down, in which I'm storing to a certain point. Like for each point, I'm storing like these things. Like this 6 is the left of ij, right? This 7 is the up of ij. And similarly, I have stored everything else as well, like the down and right and everything. Okay, so I'm taking the inputs of this 0 1, then I'm storing everything left, up, right, and down. I'll show you the code for left, how it's working. Basically, left of ij is equal to whatever value is there, right? So if it is 0, then obviously it is 0, otherwise it is 1. And then if j and this thing, right? So like if j is not 0, because like we cannot add the contribution of the previous index at the first index, right? So if j is not 0, we are going to and like and it is 1. So if the element at this index is 1 and j is not 0, then we can add the left of the previous one. So basically we will get how many ones are there. So it will work something like this. So if we have 0 1, sorry, something like 1 1 0 1 1 1, right? So here we will just store 1, here we will store 2 because this is 1 and this is also 1. Then here we will store 0, then 1 2 3, right? So you can see that the lefts are being stored very correctly, right? So that's what I did here. Then I have an answer, and yeah, so I'm calculating for all the 8 directions separately. So this should work. Like up should be greater than 1, right should be greater than, sorry, let's see the up and left one, because only that's the one that I have explained in my drawing board. So like up ij should be, wait a second, left is the smaller one, right? Let's see this one. Okay, right. So left ij should be greater than 1. Obviously the smaller side should be greater than 1. The up ij should be greater than 2. Obviously the bigger side should be greater than 2. And in the answer we add the minimum of left comma up by 2 and minus 1, because we cannot consider the segments of length 1. Yeah, so I struggled with this a little bit because like there was a lot of lines of code here. I had to change a lot of things, but yeah, it finally worked. So yeah, that's pretty cool. Now let's see the next problem. What was it? Rabbit house, right? What was it? Totally forgot the problem. Hmm. Right, yeah, this was pretty easy. I think it clicked me really quickly. Whatever time I took was encoding. I cannot watch this video right now, but I think the moment I read it, within 3 to 4 minutes, I realized what we have to do here. Right, so this was also an easy problem. I haven't really proved my solution, although the proof is like really intuitive, so you don't even have to prove it. But it's something like, right, so problem is again kind of simple. It is like you have a grid, okay? So you have a grid kind of thing, and on each grid there are some blocks that are kept. Like on each cell of the grid there are some blocks that are kept. Like let's say you have 6 blocks here, you have 3 blocks here, 2 blocks here, 5 blocks here, and so on. Right, so you have some blocks on each cell of the grid, and what's happening is basically there's a rabbit, and the rabbit will run around everywhere. Okay, so you don't want the rabbit to get hurt, so you want this thing to hold true, like the absolute value of the height of x minus height of y should be smaller or equal to 1 if x and y are adjacent. And adjacent means edge sharing. Okay, so this is just the 4 connectivity, like this thing is connected to all of this, all of these, right? So here it is fine because the absolute difference is just 1. The absolute difference between 6 and 5 is 1. But here it's a problem because if you have the rabbit here and if he jumps here, or if you have the rabbit here and if he jumps here, the absolute difference will be greater than 1. And that's not what you want, right? So to fix this thing, what you can do is you can place some boxes. You cannot remove any box, so it's like you cannot make this 6 equal to 5, that's not allowed. But you can place some new boxes and you can increase the height of anything by 1 in one move. And you want the minimum number of moves, right? So something like if you make this 5 and if you make this 5, so yeah, this becomes like you spent 2 moves here and you spent 3 moves here, so in total you spend 5 moves. And yeah, so you want to get the minimum number of total moves that are required, right? So for this, I think it is kind of easy to see that it is greedy, and that whatever the maximum height is, you will never increase that, right? So let's say the 6 is maximum in the entire grid, and everywhere else values are small. Like everywhere else you have 1 2 3 1 2 3 1 2 2 2 3 1 and 1 2 1 2 1 1 1, right? So everywhere you have small values, so you already know that you won't increase this 6 ever, right? Because it is obviously a waste of moves. You don't have to increase this 6. Right, so if you want to increase this 6, what you have to do is you have to get the elements that are adjacent to it correct. Right, to get And to get them correct, what you want to do is you want to make them at least 5. So I will make this 5, I will make this 5, and I will make this 5, right? And this entire thing will cost me what? 3 plus 3, 6 plus 2, 8 moves. Okay, so this is 8 moves. And then what I can do is now I can do the same things for all these 5s and ignore this 6 even exists, because now I know that I will never change this 6. So what I have to do is for this 5, I have to make everything 4 around it. And yeah, so that's exactly what you have to do here. Start from the biggest element, then make everything around it big enough, then forget that it exists, take the next biggest element, make everything around it you know uh, big enough, and keep on doing it, right? And if you had 2 6s somewhere, like if you had another 6 here or something like that, so you have to start from here as well, right? So yeah, so you have to start from all the places, and yeah, something like that. Okay, that's what you wanted to do, and that's exactly what I've done in my code. Let's see. Okay, so this is the problem. See, yeah. Okay, you can see that I have the graph moves. So these are nothing but the graph moves. And what I mean by the graph moves is that any pair of dx comma dy will give you a move in the graph, right? So this is like 1 0. Actually, it's like 1 0, 0 1. Then you have minus 1 0 and 0 minus 1, right? So these are just the graph moves. Then I take the grid as input. I have a set, right? So this is like a set to find the biggest quickly, right? So what I will store in this set is the negative of height, like the minus height, comma x comma y, something like this, right? So this will give us the element with the maximum height, because the element with maximum height will have the minimum the element with maximum height will definitely have the minimum negative height. Instead of putting it negative, I could have also done something like greater pair int pii, something like this. Even this I could have done, but I thought it's convenient to just put it negative. I don't know why. Like both are equally fine. Maybe this is a little bit more work. I don't know. So while the set is not empty, I take the top element of it. I get the xy from it. I run loop for 4. So this is just the graph moves. The 4 connected graph moves. If I do the 4 connected graph moves, I get the new x and new y. If it is out of bound, then I continue. If the height is already greater than the height that I want to make it to, then also I continue. Then I take the difference between the heights. And I am not taking absolute difference because I already know that height minus 1 is greater than this thing, right? And this thing I'll add to my answer, because these many new boxes I want. These many boxes to be put on top like this. And yeah, so then I erase the previous entry, I update the height, and I insert it back into the set again. And yeah, that way it will work, and I'll just print the answer. And it ran, got me accepted. I was able to do it pretty quickly, I think. Like I did this at 18 minutes, and then within 9 to 10 minutes, I was able to do this problem. So I was able to do this problem quicker than B. Like I was able to do C quicker than B. Yeah, that's a nice thing. Mm. And then I have this checksum. Okay, so that's the only thing that's left. Yeah, so this was kind of interesting. I think it was really interesting because the funny thing here is, like, you don't even care about these R's and C's, right? So let's see why. It's like there are two people, they have n cross n Boolean matrix. By the way, a lot of time I spent on debugging, because like I don't know how much time I spent on it, but it must have been at least like a lot of minutes. I'm pretty sure about that because I spent a lot of time. I didn't even realize that this is a square matrix. So you can see here that I have r comma c and I take r as input and I put c equal to r. So I didn't know that this is a square matrix. I thought we are given both r and c and we have to take both as input. So because of that, it was giving me the really strange output because like um, like the c I was taking as input, it was giving me the first element of the matrix and everything got shifted by one, and yeah, it was really messy. Okay, so I wasted a lot of time on that. So yeah, that's one thing that you can learn. Just read the input format really carefully. Okay, so you are given a Boolean matrix, and okay, you're not given a Boolean matrix. I mean, there is a Boolean matrix that is kind of hidden, and you're like they decide to note down the checksum, which is just the bitwise XOR of each row and column, right? So it's like you take the bitwise XOR of the row, you take the bitwise XOR of the other row, the bitwise XOR of the this row and so on, right? Something like that. And checksum of the ith row is represented as this thing, and checksum of the jth row is represented as this thing, right? So you are given this also as input. Let's see what the input is. So something like the number of test cases, then a single integer n, that is the size of the square matrix. Then, right, n integers representing matrix A, jth element is aij, right? So this is just the matrix A. Then there's something B. I'll come to that later. What B is, and the next line contains n integers that represent the R and C. Okay, the checksums basically. And once they finish the matrix, however, due to a virus, some of the element in the matrix got replaced by -1. Okay, so some of the element got lost, and luckily, Edgar still remembers the checksum values. He would like to restore the matrix and reaches out to Grace for help. After some investigation, it will take bij hours to recover the original value of aij. Okay, so if you want to get the original value of a certain cell, you have to spend a certain number of hours. And given the final matrix and the cost matrix, checksums, everything, so everything you are given everything, right? You want to find the minimum number of hours needed to restore the original matrix, right? That means you want the solution to be unique, right? So something like let's see this one. You see, there are multiple solutions here. Like if everything is -1, we can have multiple ways to fill this matrix. But we want the solution to be unique, and that unique solution will be the solution that is originally like that was originally present with Grace and Edger. Okay, and it is guaranteed that there exists at least one way to replace this thing. Okay, so there is at least one way that will satisfy RNC. And yeah, that's what we have to do. We want to bring the minimum cost. So you can see in the first sample when it is given like 1 minus 1 0 and like there's only a single -1 in the entire matrix. So what's happening is we don't have to recover this element, right? Why don't we have to recover this? Because we already know the XOR of this entire row. So from that we can easily get this element, right? So from the XOR of the row we can get this element, and in that way we are able to get the matrix, and we don't have to spend any money, right? So the answer is 0. But in this example, what's happening is if you don't recover any single cell, what will happen is you will have multiple solutions. Like I think one solution is 1001. The other solution could be something like wait a second. I think one solution is, I don't know what the solution is, but obviously there can be multiple solutions. If you if you flip all of the elements, definitely that will also be a solution. So something like if I'm using the wrong pen. Okay, but yeah. So if you have a solution that is let's say if ABCD works, right? So obviously not A, not B, not C, not D will also work. Let's see why. Because the XOR of these two elements and the XOR of these two elements is exactly the same, right? You can even see, because A XOR B is nothing but A B complement plus B A complement, right? And if both were already complemented, it would become nothing but A B B complement plus B complement A complement, that is equal to A complement B plus B complement A, which is equal to I think if we regroup it a bit, it becomes the same thing, AB complement plus BA complement, right? So that means these two are equal. So obviously, if you have four elements like this, it will definitely be wrong. So that's the main idea here. It took me a lot of time to realize this, but that's all that is. Like if anywhere you have four elements like this, like they're in the same row, in the same column, and anything like that, we don't even care about the values of the checksums, right? We don't care what the checksums are. Anywhere if we have four values like this, if ABCD will work, then not A, not B, not C, not D will also work, and we won't have a unique solution. And to get a unique solution, we want to break all of such cycles, and we want to basically make a forest or a tree out of it, right? And we only care about the elements that are -1. So let's say if we have something like this, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, something like this, right? So what we have to do is we have to make a graph. These two have an edge, 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 and like there can be a lot of edges, like too many edges, maybe n cube edges in total, right? So obviously that's a lot. So I'm telling you already that this won't work, right? So this won't work. But yeah, if we make all of these edges, what we have to do is we have to remove the minimum number of vertices such that whatever's left is acyclic, and the total cost of whatever is left is the highest, right? So even this problem is really difficult, um, um, even if the number of edges or vertices are less, even then it is really difficult. And right now it's already difficult, right? Because the number of edges are already too much. So usually in these cases, this is like a common observation. I don't know why it didn't click me sooner, but there's a cool thing that we do here. So instead of connecting this to all of these, what we do is we kind of connect this to like we'll number the rows. Okay, so we'll number it R1. Sorry, these are columns: C1, C2, C3, C4. We will also number the rows like R1, R2, R3. Instead of connecting this to this, what we do is we connect this to R1, and then we also connect this to R1, this to R1, this to R1, this to R2, this to R2, this. Okay, so like this we make an extra vertex for this row. For each row and for each column, we make extra vertices and we connect them like this. Okay, again it's the same thing, just the number of edges are less now. The number of edges are like 2n square now, which is manageable, right? So we can now work with 2n square, but still the problem is really difficult. It is something like um, you know, you are given a graph with a lot of edges, and what you want to do is you want to remove some of the vertices such that the graph becomes acyclic and the total weight of the remaining vertices has to be the maximum. So it is still very difficult, but what we can notice here is a very good observation here actually. So we had something like this, right? Okay, so you can see for this element it has only two edges, exactly two edges, one with R1, one with C1. Okay, similarly even this vertex has only two edges, one with R1, one with C2. Even this vertex has only two edges, one with R3 and one with C3. Right? So what we can do is we can totally get rid of this vertex and we can directly connect R3 with C3, right? With the weight of removing this vertex, right? So we will use this thing to basically get the get a graph between these rows and these columns. So that's what we're trying to do here, right? So since we have a -1 here, we will connect these two. We have a -1 here, we will connect these two. We have a -1 here, so we will connect these two, and so on, right? So this will become a bipartite graph because no two rows are connected and no two columns are connected. So it would look something like this. On one side you have a lot of rows, one side you have a lot of columns, right? Something like this. It will work for a non-square matrix as well, but yeah. So you have a lot of rows on one side, you have a lot of columns on one side, and then you have edges in between them like this. Okay, and yeah, so these edges have some weight. They have some weight. Let's say the weight is equal to wait a second. Weight is equal to the, like, comes from the B matrix, right? So B matrix gives us the cost of recovering, like this thing gives us the cost of recovering a certain value, right? So the weight comes from comes like B matrix elements. It comes from the B matrix elements, and yeah, so you have something like this. And let's say in such a graph, what would uh, cycle would look like? Let's say if we have something like this, -1, -1, -1, -1, 4 elements like this. So what would it look like is, let's say from a certain row R2, let's say this is R1, this is R2, this is C1, and this is C2, right? So from R1 there is an edge to C1, yes. From R1 there is an edge to C2 as well, right? So I made this edge, I made this edge. Now let's make this edge. So this is from R2 to C1, and this is from R2 to C2, right? So you can see this is like a cycle in the bipartite graph, and any type of cycle is harmful. Even if you had something like this, right? So this is also a cycle, this is also harmful, and you don't want cycles to be there. Even this will look like a cycle in this graph. Let me show you what it would look like. It would look something like from R1 you have edge to C1 and C3. From R2 you have C2 and C3, and from R3 you have C1 and C2, right? So again you have a cycle like this. I'll draw from with red how the cycle is formed, like R1 to C1 to R3 to C2 to R2 to C3 and back to R1, right? So you have a cycle. You don't want any cycles. Basically you want to remove all the cycles, and to remove the cycle it is simple. You have to make it a tree, and you want the tree with the maximum weight because you want to remove the edges of the minimum weight, like the total weight of the edges that you have removed has to be minimum. So the total weight of the edges that are remaining has to be maximum. So you want to make the maximum spanning tree. So you have to make the maximum spanning tree. That's what you want to do. For this you can use two algorithms. One is the Kruskal, the other is Prim or Pim, I think. Let's see. I'm not very sure what the name is. I typed it out here because I don't want to type P on my address bar. Anyway, Prim algorithm. Wait a second. Prim algorithm. Yeah, it's Prim algorithm. Right. So Prim algorithm can be used to get the minimum spanning tree. It can also be used to get the maximum spanning tree. That's the one I used. You can use Kruskal also here. Kruskal, I think Kruskal might be easier here, but you will have to write DSU. Right. So for Kruskal, you need to know DSU and you have to code it. I had a snippet of it. Maybe Kruskal would have been easier. I'm not very sure. Yeah, I think Kruskal would have been easier. I don't know why I use Prim, but anyway. So yeah, I think I'm just more familiar with the Prim algorithm, and that's what you wanted to do here. You can see my code. I take the inputs, right? And yeah, then I make the graph. So I'm joining each row to each column. If this Aij is -1, then I'm joining a certain row to a certain column. And to represent both the rows and a column in a in a single adjacency list, I kept a constant, like big constant. It doesn't have to be really big, just bigger than number of rows. Okay. So you want capital R to be bigger than the number of rows. Then I make the adjacency list here. Okay. This is the visited, because you need visited for prim algorithm. Okay. And yeah, when I'm taking inputs, like when I'm taking the cost as input, if this is -1, I'm making the edge between I and j plus r. Right. So r is big enough to make sure that no two rows and column get the same index. Right. And I'm taking the total weight of all the edges, and I will print the weight of the MST total minus the weight of MST, right? So this will be the minimum that has to be recovered. Prim algorithm is kind of simple. You can learn about it from anywhere. Just what I'm doing is it's very similar to Dijkstra, just that instead of putting the distance in the set, we just put the weight of the edge in the set. So you can see we just put the weight of the edge in the set. I'm putting the weights as negative because we want the maximum. Negative weight, so we get maximum. And rest is similar to Dijkstra, right? So that's it. And we wanted all of the sources to be in the set, so I'm just putting 0 comma the row, so that we have all the sources in the set. And yeah, that's it. That's what we want. We want to get the minimum spanning tree, sorry, the maximum spanning tree, and that's it. So I was able to do it. I got wrong answer one time, and that was because, so when I got wrong answer, the code I was writing is basically something like, this second. Yeah, I was getting wrong answer because I was choosing only one start point, and only that starting point I was putting in my set, and then I was working with that. So it ran on the sample because there is only one connected component in the sample, but there can be multiple connected components. It could look something like this. Let me show you. Right, so it could look something like this: -1, -1, 0, 0. Then again you have -1, -1, 0, 0. Then you have 0, 0, -1, -1. Right, and again you have 0, 0, -1, -1. So you can see these two components are not connected, but you have to solve for each of them. So that's the mistake that I was doing here. And to fix that, what I did is I removed this part. I took this part upwards like this. And instead of just storing the start, I'm pushing everything to the set. So s dot insert 0 comma I, right? And then it worked. So yeah, that's it. Probably my rank is still 29 because it can't change now. Right, 29th. And let's see how else people did in India. Aditya said he's also a friend. I don't know this person. Then I don't know anyone else. Oh, okay, I know Varnier. It's from IIT Roorkee. He's also a friend. Okay. I don't know a lot of people here, but I know Aryan. He's from IIT Kanpur final year. So anyway, thank you for watching, and we'll I'll be doing the Kickstart rounds for. I'll be doing this type of solutions and Screencast for all the contests, all the Kickstart contests this year. and thank you for watching.